took the pair of skew lines and looked at a general quintic that goes through them. Maybe show that thing as non-zero.
I'm sharing. Okay. Are you ready? Okay. Welcome everyone to the second lecture of Griffiths Harris about the positivity in Hodge theory and algebraic geometry.
Thank you. So today what I'd like to do is to give some illustrations of how the curvature of the Hodge bundles enters into using those to draw conclusions about families of Hodge structures and therefore about the cohomology and families of algebraic varieties. The general philosophy is that if you have, there are two parts to it. One is that if you have a family of Hodge structures over a quasi-projective variety, then the bundles that you think of normally, the canonical bundle or the log canonical bundle, the log cotangent bundle, tend to have negative curvature. And the statement is precise if the Hodge structures vary non-trivially to first order at each point. In general, if the Hodge structures vary non-trivially at a general point, then you're going to get negative curvature, but with some degeneracies that I'll explain in a minute. But negative curvature means things like hyperbolicity and stuff like that. Okay? So that's the sort of philosophy. And the computation ultimately comes down to the following sort of simple-minded observation. If you have a Hodge structure which is polarized, so it has two bilinear forms. A first bilinear form, which is an equality, it's a quadratic form that expresses orthogonality of the PQ spaces in the Hodge decomposition. And then the Hermitian form, where you conjugate one of them, has a sign. The sign is, it alternates when you move in the Hodge decomposition. It alternates with when HPQ goes to HP minus 1, Q plus 1, you get one sign, and then you get a different sign for the next step. So the signs alternate. What that's going to imply is that the curvature, so once you have vector bundles with metrics, then there's a canonical connection and curvature. And the alternation of signs in the second bilinear relation will mean that the curvature is a difference of positive terms. And those then can be used in algebrogeometric arguments, as I'll illustrate. So that's the sort of general philosophy. That's the first part. The second part is most families of algebraic varieties have singular ones in them. The usual mechanism, you can assume you have a quasi-projective parameter space for the smooth ones with a normal crossing variety where the singular ones appear. And the general philosophy is that the Hodge metrics, first, that the Hodge bundles extend canonically to vector bundles on the completed parameter space. Secondly, is that the Hodge metrics will degenerate, but only logarithmically. So once the bundles extend, you know what sections should be across the divisor at infinity. So a natural question is, well, what about their Hodge metrics? And the answer is that they're bounded logarithmically, both positive and negative powers of log. And that's the metric, and that the curvatures are the intrinsic invariants from the curvatures. Those are usually the Chern forms, the elementary symmetric functions of a curvature, that those are bounded by expressions that are no more singular than you get from the Poincare metric on a product of punctured disks. Okay. So you don't get exactly Poincare metrics, but you get boundedness in terms of the Poincare metric. The Poincare metric on a puncture disk has constant negative curvature -1 to normalize it. And it has rather remarkable geometry that will then have Hodge-Riemann and algebraic geometric significance. The first is if you look at circles around the origin, shrinking to the origin, the length of those circles goes to 0. And the area in the Poincare metric of the puncture disk is finite. You have a singularity at the origin, but the differential forms are integrable and you have finite area. So the fact that the lengths of these circles tend to 0 is going to translate into a proof of the local monodromy theorem. The fact that the Poincare metric has finite area is going to translate into saying that the volume forms that you get on parameter spaces for families of algebraic varieties have finite volume, even including finite volume, even though it's an open variety. The singularities don't cause the singularity, don't cause the volumes to blow up. And that's going to mean by a standard theorem in complex analysis that says if you have an analytic variety defined in the complement of a proper subvariety, and if you have finite volume for the analytic variety, just think of the whole thing as sitting in some open set in Euclidean space. Use the Euclidean metric to compute volumes. So Bishop theorem says that if you have finite volume in the for the analytic variety, so if it has singularities, take out a proper subvariety. If that has finite volume, then the closure of the original one is an analytic variety. No essential singularities appear. Okay? So what that's going to translate into is saying that, for example, if you have a holomorphic mapping from an algebraic variety to the parameter space for a family of Hodge structures, that mapping is rational. No singularities at infinity. So it's sort of big Picard type phenomenon. So let me try to explain some of that. Beginning with volume forms, a volume form is locally a multiple of the Euclidean volume form with a positive function, a non-negative, it can have zeros, and poles. So it can be product of a positive C infinity function, the norm squared of a holomorphic function, so that's then to be degenerate on the zeros of F, and then a polynomial in logs of analytic functions. Those are the volume forms that you will get from Hodge theory, and therefore from families of algebraic varieties when you look at their Hodge structures varying. Those are the sorts of singularities that you'll see on the volume form near the divisor that you take out. So in the case of the volume form, this coefficient function will be integrable, so you have finite volume. And since it's integrable, you can take its derivative as a distribution. And the Ricci form is this, by definition, I over 2 pi times dd bar log of h. That's the Ricci form. It's a closed 1-1 form, 1-1 current. Current being, if you, roughly speaking, differential forms with singularities that are not too bad, so you can still integrate them against any smooth function and get something finite. And will represent, since it's a closed current, it'll represent the Turing class of the canonical. So given a variation of Hodge structure with a d-dimensional parameter space, and where the Hodge structures generically vary non-trivially, the differential of a period map is at a general point 1-1, then you have a volume form. and you have the canonical extension. So the volume form, the omega, is the first Chern form of that line bundle. That's the product of the determinants of the FPs raised to the power P as your tensor product over all the P's. So it's like taking the determinants of the vector bundle in the Hodge decomposition and raise those to successively lower powers as you move down the Hodge decomposition. That bundle has positive curvature where the differential is injective. Yeah. So that's the volume form that you use, the first Chern form of that line bundle that was on the overhead yesterday. So it's a calorimetric on the points where the differential is injective, and the usual Ricci form with the Ricci curvature of this calorimetric is the negative of the Ricci form. These sign conventions got put in years ago, and I think they're sort of standard. So positive canonical bundle means Ricci form positive. So the conjecture, which is only parts of which it has been proved, is that the Ricci form is first the Ricci form of the pure volume form that you get where the volume form is non-zero, it's positive. And there are two types of correction terms, the divisor at infinity and R for ramification. And to explain how to think about this, go back to the example of P1 minus 3 points. So the universal cover of that is the disk with the Poincare metric. So on P1 minus 3 points, you have a metric of constant negative curvature. We'll see that the singularities at the puncture look like Poincare type terms plus lower order stuff. Now take a holomorphic map or a map from an algebraic curve, non-compact, into P1 minus 3 points and pull the area form on P1 minus 3 points from the non-Euclidean metric, of the one of constant negative curvature, pull that back. So you're going to get this for its curvature, that'll be a negative term. Z, R is the ramification, where the volume form, where the map ramifies, the volume form has singularities, it goes to 0. That's the ramification term, and Z is the divisor at infinity. Okay. So we skipped a bunch of slides here.
Can we go back?
So this is it's an outstanding problem. As I say, parts of it have been proved in special cases, but it's not known in general as far as I know. And this is just repeating what I said earlier about the singularities of the curvature. So here, to explain a little bit more what's going on, the Ricci form of the volume form, where it's positive, extends to the closure of Y as an L1 differential form. but in the Ricci of the Ricci form, you have to add delta functions. So if you go back to the formula, you have the usual Ricci form, and then you have a contribution from the ramification, and then a negative contribution from the singularities. So these are illustrated in this example. Just take the Poincare metric on the punctured disk. It's integrable, and the Ricci form is the form itself. So negative curvature means positive Ricci form. On the completed disk, the Ricci form is the Poincare metric plus a delta function at the origin. That's the singularities. So that's the Z that was in the previous, in the statement of the conjecture in this case. This is just repeating what I said earlier about the curvature of Hodge bundles. The positivity properties are, if you have everywhere non-degenerate curvature form, I'll define that in a minute, then you're going to get real positivity in the usual sense of line bundles and vector bundles. But in general, when the differential of the period mapping is only 1, 1 on the Zariski open, then you're going to get, instead of real positivity ampleness, you're going to get bigness and neftness, those two. And most examples, that's what you have.
Yes. Is this known, for example, for locally symmetric spaces? Like, is this known for like for the cases of locally symmetric spaces that parameterize variation of Hodge structures, like this conjecture? For example, is this known for?
So, yeah.
Okay.
So here, instead of the canonical bundle, I'm going to look at the log tangent bundle. So Y bar is the smooth completion, Z is the normal crossing divisor, and the differential of the canonically extended variation of Hodge structure is just this map that's induced by the Gauss-Menin connection. That's what the theta usually denotes. So the canonically extended has a local Torelli that this is everywhere injected. So that's not just in the Zariski open, but it's also on the divisor at infinity. And then the question is, does the local Torelli property imply that the log canonical bundle is ample? And one can show that it's big and nif, but ampleness, so far as I know, is not known. And this is just a reference to some work in the literature, which I'm not going to go into. I will say that the issues are related to those that were mentioned in conjecture B, trying to understand the geometry of the limiting mixed Hodge structure. So remember that P was the image of a period mapping. Conjecturally, the closure of P is a Zariski open and a complete variety, P bar, that's canonically defined, sort of the minimal Satake-Bailey-Burrell completion of a period mapping. And you look at what happens on the boundary. So you have limiting mixed Hodge structure along the strata. And when you have a limiting mixed Hodge structure, you have, of course, the associated graded. So whenever you have a mixed Hodge structure, you have the associated graded. Those are pure Hodge structures. And then you have the extension data. There's a lot of geometry. In fact, in some ways, it's even richer than that in the Hodge structures themselves, you have a lot of geometry in the extension data. So for example, the basic example of extension data is take a smooth algebraic curve, take a divisor of degree 0 on it, and look at the mixed Hodge structure on the complement, the curve minus the support of the divisor. Take out a bunch of points. That mixed Hodge structure has, as its associated graded, the Hodge structure of the cohomology of the curve and the Hodge structure of these points. That's just the constants for each point. The extension data is the mapping of the curve to its Jacobian variety given by that divisor. So the geometry of the curve sits in the extension data. That's sort of an illustration of the general way to think about extension data. One of the interesting points about extension data of limiting mixed Hodge structures, not just Hodge structures, but of limiting mixed Hodge structures, is that the extension data has only two levels. You have first the extension between between the associated graded that are in adjacent weights. And then you have the extension data between Hodge structures where the weights jump by 2. So think of the projected line with a bunch of points. The mixed Hodge structures are degrees 0 and 2, and the extension data then is going from something of weight 0 to weight 2. So it jumps by 2, stops there. There's no higher extension data in a limiting mixed Hodge structure. So this extension data is the issue is to convert information along the fiber to what happens to the normal bundle of these divisors at infinity. And there is a conjecture here that if you make a local Torelli assumption, that is the differential of the period map at infinity is locally 1, 1, then the conjecture is that the conormal bundle on the strata of, that's what the notation there is supposed to designate, that the conormal bundle on the strata is ample. So intuitively, if you had your divisor at infinity and you blew stuff up, then you're going to get that the limiting Hodge structures don't change on the blown up stuff. So you're never going to get ample conormal bundle. But if the Hodge structures the limiting mixed Hodge structures are really varying along the strata, then the conjecture is that you get ample conormal bundle. And I think I will skip this. Yeah. Turning to symmetric differentials and hyperbolicity, and there's a nice seminar going on about this here. It's a seminar that we had just a few weeks ago. For holomorphic vector bundle, the notion of big means that, well, the first is that for high enough power, symmetric power of the bundle has enough sections that generate all the fibers. That's going to mean that the vector bundle is itself positive. If they generate all the fibers outside a closed subvariety, so at a general point, that's going to mean that it's big and Neff. So to explain that a little more, if you have any vector bundle over a complex manifold, you look at the projected bundle of hyperplanes in the fibers. So this is what the fibers are. There's the tautological line bundle. And the vector bundle is big if this is big in the sense of line bundles. So that's just repeating a definition. Suppose now you have a Hermitian metric whose curvature form is semi-positive. So the curvature form is a bilinear form. One entry is a point in the fiber, and the other entry is a tangent vector. So it's a curvature form associated to a curvature tensor is this bilinear operator. And then the limit that I just mentioned is that suppose that the curvature form is generically positive, then the vector bundle is big. And here's the definition of the curvature form. The curvature operator, it's an endomorphism valued 1-1 form. So it's a matrix valued 1-1 form. That's the curvature tensor. And so you have a curvature operator. Take the value on E, inner product E, evaluated on a tangent vector wedge's conjugate. That's the definition of the curvature form. And the geometric interpretation of that curvature form is the following. You take your vector bundle with a metric and look at the associated projective bundle. That thing has a line bundle. And there's a canonical metric in that line bundle on the associated projective bundle induced from the metric on the original vector bundle. What about the Chern form of that line bundle? Well, the Chern form along the fibers, you're just looking at the O of 1 bundle on projective space. So its Chern form is the usual Fubini study form, it's positive. So this line bundle has positive curvature along the fibers of the projective bundle. What about the horizontal direction? Horizontal is well defined because you have a Hermitian form that's positive definite on the fibers, so the orthogonal complement to the tangent space to the fiber is well defined. It's a well-defined horizontal space, and that's what the curvature form measures. So the curvature form is the Chern form of this line bundle, the OP1 line bundle on the horizontal spaces. So if you have positive curvature of the vector bundle, that translates into positivity for the Chern form of the O of 1 bundle on the projective bundle, and that's an ampleness type or bigness and netness type statement. In the situation at hand, we're going to look at the logarithmic tangent bundle of the completion. And we discussed that this has a metric that's singular. The Chern forms are expressed in terms of differential forms that represent the Chern classes in cohomology. And go back. Right. So that's a general statement about any vector bundle, any of the Hodge bundles. What about the tangent bundle itself? So not a Hodge bundle itself, but the tangent bundle. It still has a metric induced from the Hodge theory. That's the Chern form of this canonical line bundle L. So you have a metric in the tangent bundle, and you want to know that the singularities of that metric in the tangent bundle, not a Hodge bundle now, but the tangent bundle, the log tangent bundle, that those are similar, have similar singularity properties to those for the Hodge bundles themselves. That's not known. It should be true, but it's never been established. One thing about these curvatures is that it's always used, so a philosophical reason, is the deviation of the curvature for the induced metric from the restriction in the endomorphism is of this form, where this is a matrix of 1-0 forms. So the curvature of the log tangent bundle with the induced metric is more negative than what's induced from this. So that means that the signs go the right way to increase the bigness of this thing with A. So the results that were stated earlier in the first lecture that are known, A and B, one was dealing with bigness of the logarithmic canonical bundle, and one with bigness of the logarithmic tangent bundle. Those are both proved by these types of arguments here. Turning to hyperbolicity, there's one amazing result that always is used in some form or another that I know of, which is the Schwartz lemma. So if you remember the Schwartz lemma from one complex variable, it says that if you have a holomorphic map of the disk to itself, so you have an analytic function defined on the disk whose norm is less or equal to 1, and which takes the origin to the origin. So f of 0 is 0, and the norm of f is less or equal to 1. What was the statement that I wanted to make? Yeah. I'm sorry. The Schwartz lemma is that if you have the analytic function on the disk, the Schwartz lemma says that if you have the analytic function mapping the disk to itself, taking the origin to the origin, then the norm of f of z is less or equals z everywhere. That's the standard Schwartz lemma in one complex variable. Interpreted intrinsically, that says that you take the Poincare metric on the unit disk, the metric of constant negative curvature, and the Schwartz lemma then intrinsically tells you that any holomorphic map of the disk to itself decreases distance in the Poincare metric. It says exactly that for the constant negative curvature Poincare metric on the disk, any map of the disk to itself is distance decreasing. That's the Schwartz lemma. I remember I said fix the origin to be the origin. Now take any linear fractional transformation and apply, and use the invariance of the Poincare metric under linear fractional transformations, and that gives the metric, or the geometric, differential geometric state that I mentioned. So the all-four Schwartz lemma, so first it's dealing with the pseudometric on the disk. That's the sorts of things that you would get when you have ramification. And this is the Ricci form. The definition of the Gauss curvature of the Ricci form, or the curvature, in the one-dimensional case, the Gauss curvature is this. That's the usual Gauss curvature of the pseudometric. And at points where you have ramification, you set it equal minus infinity. The Poincare metric is this. Constant negative Gauss curvature translates to the Ricci form equal of the Poincare metric equals the Poincare metric. The all-fours lemma, I think, keeps disappearing. The all-fours lemma says that if you have an omega whose curvature is less or equal to minus 1, so that's any metric on the disk, Hermitian metric, so 1, 1 form, whose Gauss curvature is less or equal to 1, minus 1, then the form itself is underneath the Poincare metric. So the ratio of omega bigger than or equal to omega, that's Gauss curvature less or equal minus 1, means that omega is bounded from above by the Poincare metric. So whenever you have negative curvature, then you're going to get bounds on what the metric can look like. So for the little Picard theorem, for example, if you have a holomorphic, if omega is defined on a disk of radius r, then you're going to see that there is no metric on the whole complex plane with negative curvature everywhere. That's just reformulation of the Alford's lemma. And this is just a proof of the Alford's lemma. It's a very simple application of the maximum principle. And the Alford's lemma is everywhere in this story in hyperbolicity. So the standard corollary is if you have a complex manifold with a Hermitian metric whose holomorphic sectional curvatures are negative bounded from above, then any holomorphic map from the C into M, no entire holomorphic map, is non-constant. And the application is if you have a variation of Hodge structure whose period mapping has injective differential, then any holomorphic map to the parameter space is constant. That's because the curvature of the tangent bundle, which I mentioned earlier yesterday, that has negative holomorphic sectional curvature. If the differential is only injective one, there's a risky open, then the image of such a holomorphic mapping is in a proper subvariety. And this is just a comment on the relation between symmetric differentials and holomorphic hyperbolicity. And it says if you have a lot of symmetric differentials, you can construct a Finsler metric like this, and tends to have semi-negative curvature where these sections generate the fibers. And so there's also a logarithmic version of all this. There's some, in the slides, there's some references to literature about this. For the big Picard theorems, again, recall that the big Picard theorem says that in one complex variable, the simplest version says if you have a map of a punctured disk into P1 minus 3 points, then it extends across the origin. Or if you have a holomorphic map of an algebraic curve, non-compact, to P1 minus 3 points, then it's a rational map, because it extends across the missing points. So in general, and here this is what I just mentioned. And if you take any completion of Y, your parameter space for your family of Hodge structures, if you had information on the Kähler metric given by the Chern form of that characteristic Hodge line bundle, the product of the tensor product of the determinants of the FPs, then the result would follow. And I just give a reference to some of the literature about this, in particular the use of Neven-Luna theory, which, those of you who know it will recognize the statement. Neven-Luna theory says that any holomorphic mapping defined on the complex plane or any meromorphic function defined on the complex plane can omit at most 2 points in its image. So the Neven-Linde defect counts the number of times a point in the projective line is hit by a holomorphic map from C to P1. So the Neven-Linde counting function just counts the number of points in the inverse image. It's a function, you're looking at it in disk radius r, so it's a function as r goes to infinity. And the defect of a point in P1 represents those points that are hit less often than they are on the average. It's usually denoted delta of A, where A is a point in P1. The basic theorem in Neven-Linde theory says the sum of the defects over all points in P1 is less than or equal to 2. If you don't hit the point at all, the defect, there are no points, so the defect is 0. So it's a vast generalization it's a qualitative version of the Picard theorem. And I think it's just beginning to be used in Hodge theory. Some of the references that I gave use this to draw sort of qualitative information on how a picture really of what the graph of a period map or a family of Hodge structures will look like. And Hermann Weyl, he with his son wrote a book on Neven-Linde theory, and he said that it was the jewel of mathematics of the last century. I'd like to close discussing the Iyataka conjecture, which brings in a new aspect of the curvature of Hodge bundles. So in this part of the talk, the varieties will all be complete. I'll drop the X bar. You have a mapping between complete varieties, smooth, projective, and you look at a general fiber. The conjecture, which is now a theorem, is that the Kodaira dimension of the total space bigger than or equal to the sum of the Kodaira dimensions of the base and the general fiber. So I'm going to talk a little bit about this and how curvature enters into the original argument. There are arguments now that get rid of curvature, but the original argument was based on curvature considerations. The original argument by Vivek was completed by Kolar. So I'm going to discuss this in an essential case, but making simplifying assumptions. So first, that the Kodaira dimension is equal to that of the dimension, so that fibers are general type. Secondly, that the fibers move in moduli, that is, when you vary the fiber and you look at the Kodaira-Spencer map, that's injective. So it says that the differential of the variational complex structure should be everywhere injective. Just explain that Kodaira-Spencer map should be injective. So what we're going to show is that the direct image of some power of the relative canonical bundle is big and net. So that's the result that will imply the Iyataka conjecture. So that means that for sufficiently large M, the determinant of the canonical bundle along the fiber raised to a high power has lots of sections. That's really what it amounts to. Yeah. How does Hodge theory enter in the picture? Let's just first suppose that all the fibers are smooth and that you have a suitable version of local Torelli. Local Torelli means that to first order at every point, the variation of the complex structure is captured by how its Hodge structure varies. And the suitable version says that you don't look at the whole Hodge structure, just the end piece, the part coming from the holomorphic differential. So in the Hodge decomposition, that's the first factor. So the local mapping from the parameter space to planes of this dimension in a vector space, a fixed vector space, which is the cohomology or locally fixed. And local Torelli means this mapping should have injective differential. Then, under that assumption, the determinant of the relative dualizing or relative canonical bundle is actually ample. So this is a vector bundle with this fiber, space of Golomorph. Along the fiber, it's the space of holomorphic end forms, top degree forms. And this is the Hodge metric in this case. You take the form and wedge it with a conjugate and integrate. So that induces one in the Hodge line bundle, which is the determinant. And the theorem will follow from Kadara's theorem if we can show the curvature form for this line bundle is positive. So to prove that, let's just look locally at the mapping to the Grassmannian. The curvature computation from the slides yesterday, the curvature of the Hodge bundle, will tell you that the curvature form evaluated on a tangent vector, this should, I don't know what the wedge is doing there, but that's the curvature form in the vector bundle whose fiber are the holomorphic sections of the canonical bundle along the fiber. So the curvature computation from yesterday is that the curvature form is just the norm of the differential of this map. So that means if the differential is everywhere injective, then if the curvature form is positive, the differentials, well, if the differential is everywhere injective, the curvature form is positive, and you have then a vector bundle whose curvature form is positive, and as I was explaining, that tells you that the vector bundle is ample. The O of 1 on the projective bundle is an ample line bundle. So that's a proof of the statement on the previous overhead in this special case. One of the interesting points that I should have mentioned yesterday is the curvature of the Hodge vector bundles. Usually curvature in differential geometry is a second order invariant. Think of Gauss curvature of surfaces in R3. You need two derivatives to tell you whether the surface is convex or concave and so on. In Hodge theory, the curvature is a first order invariant. So to illustrate that, just take the principle that's behind it. It's not a proof of that, but the principle that's behind it. Take projective space, take the O of 1 bundle. That has a metric induced from the metric in Euclidean space. Take its Chern form. What is the Chern form? Well, if you remember the formulas, it's C is the column vector that in homogeneous coordinates, you take dz width, the transpose of dz bar. That's the usual homogeneous divided by the norm of z squared. That's the usual Fubini study metric, what you've looked at in homogeneous rather than Euclidean coordinates. The point is that the curvature depends only on the first derivative, dz. That's a general phenomenon in Hodge theory, that the curvature of the Hodge bundles is a first order invariant. It involves the first derivative in two ways. One is the sort of differential of a map. The second is in the metric, you also have first order information. So the point, the geometric point is that in Hodge theory, the curvature of Hodge bundles is basically given by first order information, which is like the norm of an actual holomorphic mapping somewhere. So the vanishing of the curvature means that some holomorphic map is constant. That's what it translates into. It's like just like for projective space. So now let's go to the final point. Suppose that you don't know that the canonical bundle along the fibers is ample, but a power of it is ample. Then the result is that the determinant of the canonical along the fibers raised to a power is an ample vector bundle on the parameter space downstairs. So that if the Kodaira-Spencer map is generically 1-1, but not everywhere 1-1, then you just get big and Neff. There's an actual question around here that I don't know the answer to. It's relatively easy to produce big and Neff as a property of a line bundle or a vector bundle. That's a birationally invariant notion. You blow up something big and Neff stays big and Neff and so on. So it's a much easier type of property to get at than actual ampleness. Well, if you say, okay, you can't have ampleness, but can we get semi-ampleness? Semi-ample means that if it's big, then you have lots of sections of powers. As if it were ample, you have that many sections. You want to know that when you have high enough power, the sections generate every fiber, not just generically the fibers. And in the minimal model program and so on, these types of questions, the base point free property and stuff like that, keep turning up. In Hodge theory, they've not been used so far as I know, and the question is, are there natural assumptions which imply, so this is a purely algebral geometric question that I think is not known, which imply that this thing is free. You know it's big and Neff. What about free? So the argument goes as follows. You take the symmetric power of the direct image. So this is a vector bundle, take its symmetric power. Those map to the push down of the power of the canonical along the fiber. And this map is given by pointwise multiplication. So the kernel of this map is a vector bundle given by the defining equations of the canonical model. And the Hodge vector bundle is this one. So the sequence here becomes this mapping to the symmetric power, mapping to whatever the image is here. And this is when you put in the relative canonical bundle along the fiber. So the ideas that go into it are that the bundle H is semi-positive. So the symmetric power is semi-positive vector bundle. Semi-positivity positivity in general increases on quotient bundles. Intuitively, positivity means lots of sections. If you have lots of sections, then the quotient will have a lot of sections. Conversely, subbundles of positive bundles tend to be somewhat negative. So the precise differential geometric statement is that the curvature form for a subbundle is gotten by restricting the curvature form of the big bundle, subtract off the norm of the second fundamental form of the subbundle in the big bundle. So you're subtracting off stuff. It's becoming more negative. It's becoming more negative than the bundle it was a subbundle of. And this is just recalling the definition of the curvature form and what semi-positive and so forth means. And these are what I just talked about. So the main point though is that you don't have sections of the canonical along the fiber, only powers of it. So how are we going to get positivity out of that? And here you look at what's called a Finsler metric. So that's a norm, but it doesn't have the usual property of a metric. And what you do is you take a holomorphic M form, so that's a dz raised to a power m. Wedge its conjugate, take the mth root, that's well defined, and integrate, call that the norm. So that's continuous, smooth only, where there's certain properties of smoothness and stuff. But what about the curvature of this Finsler metric? So what is the Hodge theoretic interpretation of this? You have a differential form that's a section of a multiple of the canonical bundle. It doesn't give you a cohomology class on your original variety, but does it have Hodge theoretic meaning? The answer is a very nice one. If you have a section of any line bundle, then you can look at the zeros of that section, and so you take a line bundle raised to some power. Suppose you have a section of that. Take the zeros of that section and take the branch covering given by the power that you have. So if it's an nth power, you take the nth-fold branch covering. Intuitively, you have dz is a section of the nth power of the canonical bundle. So just take the nth root of the thing. That only makes sense locally where it's non-vanishing, but on the branch covering it's well defined. So this multiple differential on your original variety gives you an actual holomorphic differential on a branch cover. And what this Finsler metric is simply the Hodge metric on the branch cover. So that's where the positivity of the curvature for these Finsler metrics comes from. It's at root, again, a Hodge theoretic positivity property. And the rest of the overheads are just talking about the proof of the Iotaka conjecture by Viehweg. And I think I'll skip that. The references are in the slides that are on the website of the conference. Thank you.